Hey everybody, today we're going to be talking about Chapter 15, which as you can see deals with the properties of light, specifically the nature of light. And it's one of those things where light is just one of those things that we always generally see around us. And we maybe don't give it a lot of thought, but it is an extraordinarily important part to doing chemistry and physics and biology and engineering. There is a lot of stuff that goes into understanding light and its importance. So the first thing with light, probably the thing that a lot of people know is that light does move at the speed of light, which is 3 times 10 to the 8th meters per second. That's an extraordinarily fast number. It's like it says there, it's 386,000 miles per second, which would be fast enough to go around the Earth 7 times in 1 second. I've been thinking about light for a long time in my science career, and that still is a mind-boggling number of how truly fast light is actually going to be moving. So understand that when you deal with the speed of light, it is really, really fast, and for me, it's really hard to wrap my mind around how fast that actually is. If you think about Earth to the Sun, which is a long, long, long way, it would take light 8 minutes to get there. So that's one of the things we refer to as a light minute. That's how far light is going to travel in a minute. And it does go a really, really long way in a minute, but compared to really large distances, that's actually still not going to be moving all that fast. So if we think about light in terms of the universe, light is still pretty darn slow when it comes to how big the universe actually is. You can read that there for yourself, but light moves fast at our scale, but for the size of the universe, it moves really, really, really pretty darn slow. The Milky Way, for example, is 100,000 light years across approximately. So light years, how far light is going to travel in a year. And if you're going to travel all the way across the Milky Way, which is our galaxy, it would take you 100,000 years to do it. So that's one of those things, if you ever watch a Star Wars movie and they say they're traveling from one side of the galaxy to another, let's assume that they're traveling in the Milky Way. It would still take them a really long time to do it because that's still how fast they're going to be traveling, as they're going to be traveling at the speed of light. So even if you are moving at the speed of light and you're going a really long way, it's going to take you a really long time to do it. So a light year is how far light is going to travel in a year. A light minute is how far light is going to travel in a minute. One of the kind of interesting things about light, and not one that we're going to spend a lot of time on, but is that light is a wave, and it's also a particle. So we know that light's a wave because it does travel through space, which is a vacuum. So like a sound wave couldn't do that because sound needs particles to move. Light doesn't, but it also behaves as a particle. And when we talk about light as a particle, we think about it as something called a photon, and those are just packets of light energy. You're probably saying, well, wait a second, if it's a particle, does it have mass? And the answer to that is yes, in something called a relativistic sense. Light does have mass because photons are what we consider a relativistic light particle. You don't need to get too much into it, or don't worry about it too much, but you do need to understand that light can be both a wave and a particle. For us, light acting as a particle right now isn't going to be the most important thing. We're going to be dealing with more in terms of a wave, where it has a frequency and a wavelength and a speed and things like that. So just understand that light can be a wave and a particle. We will be dealing with it as a wave, but if you ever take some other classes or ever heard that light is a particle, that is an actual thing. So in section 2 of chapter 15, it deals with the electromagnetic spectrum, which you may have heard of before. The electromagnetic spectrum is all of the different types of energy that actually moves as a wave and moves as the speed of light. So the electromagnetic spectrum, it's just all the different types of energies that are present. The wave speed equation still works, but now instead of using velocity, we actually swap that out with a c for the speed of light, because that's how fast all of these things are going to be moving. So the symbol c, it's a constant, so that's why it's a symbol c. That's talking about how fast things are going to be moving. So the speed of light is just frequency times the wavelength. And as we've talked about before, as frequency is going to increase, the wavelength is going to decrease, and vice versa. And also, something that's kind of interesting is that frequency increases, so does the energy of the wave. So it might stand to reason that not all types of light or parts of the electromagnetic spectrum have exactly the same amounts of energy. But we could still use that equation there that we have before. So got an example problem here. I'll just make that big for a second. So we're saying that the speed of light is frequency times wavelength. We're saying that we know the wavelength, but we don't know the frequency. Well, the first thing we'd have to do there is take the 400 nanometers and we would have to turn that into meters because nanometers aren't the right units that go along with the speed. So if we have 400 nanometers, to turn that into meters, we'd say that for every billion 10 to the 9th nanometers, we'd have 1 meter. So we take 400 and we divide it by a billion, and we get 4.00 times 10 to the negative 7th meters. So now we have our wavelength in meters, and we have our speed of light, so we can solve for the frequency. So 3 times 10, times 10 to the 8th meters per second. That's the speed of light. The frequency we don't know, and the wavelength would be 4.00 times 10 to the negative 7th meters. Well, rearranging that and solving for the frequency would give us a frequency of 7.5 times 10 to the 14th hertz. So that means that a wave at 400 nanometers is going to have a frequency at 7.5 times 10 to the 14th hertz. That's an extraordinarily large frequency, but it should probably make sense because the wavelength is going to be very, 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 very small. So this would be the band of the electromagnetic spectrum. Things on here you might have heard before would be like X-rays and ultraviolet light. That's what UV is. IR is infrared, and then there's microwaves and radio waves and TV waves come on there too. And then here in this little teeny line right here, that's where the visible light would be. Okay? And as you can see, it's measured in nanometers. It goes from 400 nanometers up to 700 nanometers, where the 400s are the violets and the 700s are the reds. So we'll come back to this image in a little bit here. I just want to talk about a few parts of it. The low energy waves, the lowest of the energy waves would be the radio waves, and then microwaves, and then infrared has the most energy of the ones here. But radio waves, those are the ones for radio and TV broadcasting. Microwaves you can cook your food with. The infrared is the stuff you might have seen in heat lamps before. Interesting to know is also part of remote control. So when you point your remote at your TV, that's infrared energy that's going to be coming out of there, and it moves at the speed of light from the remote control to your TV. So these would all be low energy waves because they're going to have fairly small frequencies. The high energy waves would be ultraviolets, X-rays, and gamma rays. Ultraviolet has enough energy to burn your skin, so if you get a sunburn, that comes from the ultraviolet light that's coming from the sun. That's why we wear sunblock, to keep the ultraviolet rays away. There's actually a few different types of ultraviolet light. There's UVA and UVB and UVC. Those are different types of ultraviolet, but it all still falls in the area of ultraviolet. X-rays have a little more energy, enough that they can do damage to your skin cells. That's why when you get X-rays, you wear those lead vests, because it stops the X-rays. And gamma rays are the highest of all the energies. They're good for irradiating foods, medical equipment, and things like that. That comes from gamma ray production. So all those are different types of electromagnetic energy, and that's where we see all those different things falling on the electromagnetic spectrum. So again, here would be that entire spectrum. Again, the low energy stuff right here. Infrareds, microwaves, and radio waves. So here's your lowest energy, a little bit more and a little bit more. So visible light has a little more energy than infrared does. Sometimes that surprises people. It would also stand to reason that red light then has less energy than the purple or the violet light does down here. So this side of the spectrum would be the lower energy. Over here would be the higher energy. Then you got ultraviolet. X-rays have more energy, and then gamma rays have the most. So you can see here, this image says that the frequency is increasing as you go this way. And interesting to note is that if up here you're at 10 to the second for the frequency, so about 100 waves per second. Here you're at 10 to the 24th waves per second. So your frequency is getting much, 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 much bigger as you continue along here. It would also stand to reason that as you continue back this way, as you go from left to right, your wavelength is going to get bigger. So here we have wavelengths at 10 to the negative 16th meters, and then you're all the way up at wavelengths at 10 to the 6th meters, which is right in the area of a million meters. So the numbers that are there, we sometimes look at them and we don't give them too much thought, but those values are really, really, really big numbers, and sometimes they're really, really small numbers, depending on which side of the electromagnetic spectrum that you're on. I would expect that you can know the colors of light, the Roy G. Biv going across here, which, by the way, it goes back this way, your Roy G. Biv that you would be seeing across there. So keep in mind that those are your colors of light that you're going to be seeing, with violet having the most energy and red having the least energy. Get out of this for a second, and come back to here with your colors of light. So sometimes people confuse mixing light with mixing pigments, and these are actually colors of light. It's red light, green light, and blue light. And if you mix blue and green, you actually get that cyan color. And if you mix the red and the blue, you get that magenta color. Blue and red is going to give you yellow. And when you mix all those colors together, that's actually where the white comes in. So it's different than mixing colors of pigment together, because if you mix all those colors of pigment together, you'd actually get black. Mixing light together, it actually is called an additive addition, where you actually get white light when you put all those different things together. So as far as our colors go, these are the ones that we were just looking at there. So your primary additive colors, that would be these ones, where when you mix them together, you get white in the middle. And the primary subtractive colors are when you're going to be mixing pigments together, you actually get black in the middle, because that's going to be absorbing all the colors of light. So keep in mind, mixing light together is different than mixing pigments together. You get a different outcome in what you're actually going to be measuring there. So again, we got light. Light is a wave. It can also act as a particle. Light has frequencies. It has wavelengths. We can find the frequency and the wavelength of the light. We can use our equation here, relating all those things back together. You should know the different parts of the electromagnetic spectrum. Know which side has more energy, what side has less energy. We also want to make sure that we know the different types of light that are going to go together. What specific colors you're going to get when you're actually putting those different colors of light together. Again, if you have any questions, please let me know. I'd love to help you out. If you got any questions, let me know, and we'll see you next time.